model, we end up violating the IID assumption if we ever change our behavior. So what it says is, explore the world, learn about how the world works, but never use that. Right? Never change your behavior to reflect what you've learned, because that will violate the IID assumption. You're getting data from a different distribution than the one you learned on. And it seems kind of esoteric to blame the IID assumption. It's not even a word. But, description. Sorry about that. No, I'm not going to edit the slide. But the thing is that this really happens. If you actually do this, you train up these learners, they learn about how the world works, then they start to try to exploit, and all of a sudden their predictions are all wrong and they do really crazy stuff. So this really happens. Amy's husband has a very nice paper about that, or at least it's about other things, but it has that in it. So you can say, okay, well the problem with IID actually is a bit of a problem here. Are there models that don't depend on that? And it turns out there's a whole class of algorithms called mistake-bound algorithms that have a more friendly structure. So here we imagine that inputs are being presented sequentially. On each input, the algorithm makes a prediction. What do I know about that input? And it's allowed to be wrong, but it's not allowed to be wrong too many times, right? So it's allowed to be wrong as long as it learns something significant from that, so that won't happen again. And so we say an algorithm is a mistake-bound learning algorithm if it's the case that we can bound the number of times these mistakes will happen. To do that, you usually have to restrict the hypothesis class. What kind of function space am I actually learning in? But some function spaces have mistake-bound learning algorithms, and that's a good thing. So here, the good news is the inputs can be presented adversarially. It only has to learn a label when it's actually wrong. The red boxes here are the wrong answers. And there is no particular bound on when the last mistake might happen, but the total number of mistakes is bounded. The reason that you can't bound the last time that it happens is we're imagining the inputs are presenting adversarially. So the adversary could just withhold some tricky question for infinitely long, but while it's doing that, the learner is getting a lot of right answers. So that's a great model. It's definitely relevant. The problem is you can't build a PAC-MVP learning algorithm out of that because it doesn't know when it's going to make a mistake or not. And because of that, it could make one of these asymmetric mistakes, assuming that something that's out there that has really high reward actually it's making the assumption that it has low reward. It'll avoid that, and therefore it won't be taking near optimal actions. So this is close, but it doesn't actually satisfy the near optimality assumptions. So, this is one of those combination lock environments. So we introduced a new learning model. We call it QUIC. It stands for knows what it knows. So here, again, inputs, it's like the mistake-bound model. Inputs are going to be presented online, possibly adversarially. And now, whenever the algorithm gives an answer, it has to be correct, just like up in here in the PAC model. But it's allowed to say, I don't know. It's just not allowed to say, I don't know forever, right? Because that would be a really easy algorithm class to satisfy. Print, I don't know, go back. So it has to learn from all the times it says, I don't know, but it has to distinguish the cases where it can make an accurate prediction from those that it can't. And that's really important for PAC-MVP because it means if it doesn't know what's out there, it can think of it in a happy way and go out and visit it. So what we've been doing is actually developing algorithms that are learning in environments by using...
What if it makes a mistake?
It's not allowed to. Then it's not a quick learning algorithm. Okay. Just like in the PAC setting, you could imagine that it trains up for a while and then later it makes mistakes. Well, then it hasn't satisfied. Unless it's with really low probability. It's allowed to do that. It's allowed to make mistakes with the little held out delta probability. So what we've been doing is we've been saying, hey, if we can... Anytime that we can define a class of transition functions or reward functions or Q functions that we can quick learn, we can slap an algorithm on top of that, a reinforcement learning algorithm on top of that will achieve the PAC-MVP bounds. Right? So we'll get an efficient learning algorithm that learns efficiently. And so now the problem becomes, hey, well, what classes of problems can we quick learn? So it turns out there are classes that we can quick learn. The first one is the one that I was mentioning to Eugene, which is learning the probability of a coin. So here, let's see. In general, in a quick learning task, you've got some input space X, some output space Y, some hypothesis class, capital H, where each hypothesis maps inputs to outputs. And we say we can quick learn it if the adversary is presenting us inputs, and the learning algorithm can say, I don't know, just a bounded number of times, and other than those times, always get the right prediction. So, or nearly right prediction with high probability. So coin learning is one of them. Predict the probability that a coin is going to come up heads. The observations are noisy here. It only gets to see whether it came up heads or tails. But yeah, but it has to use that information to estimate the probability accurately. And the way that you can do that is just say, the learning algorithm can just say, I don't know, a whole bunch of times. In fact, for 1 over epsilon squared, proportional to 1 over epsilon squared times log of 1 over delta, if it does that, it has enough data that it can very accurately, with high probability, estimate that probability. And that's just based on standard Huffington boundary type arguments. So that's one way to do it. And one problem that you can learn is the probability of a number. You can quick learn that. Just say, I don't know, I don't know, I don't know. Okay, now I know. Dice learning is similar, except you actually have a probability distribution over more than just heads and tails. It could be a multinomial. And in that case, you can view it as actually k independent dice, but you get a worse bound than if you actually treat the problem directly. So we have bounds for that as well. So those are very simple examples. It turns out now, if there's something that you can quick learn, there's combinations of quick learners that you can also quick learn. So for example, if you have some input space that's partitioned so that in each region, there's a quick learner for that region. But now you have to learn something for the whole space. That's not so hard. All you have to do is look at the input, look which part of the space it appears in, ask the corresponding quick learner for an answer. If it has the answer, that has to be right. If it doesn't have an answer, it says, I don't know. And then we have to say, the high-level learner has to also say, I don't know. So we can nest quick learners inside of other quick learners in the input space, but also in the output space. If you have an output that is a cross product of a bunch of output variables, all of which are quick learnable from the inputs, then you can learn the cross product. So these seem sort of like, well, sure, you can combine them in all sorts of ways, but these particular ways are really important because they get us to MVP learning. In particular, learning in MVP is really just the nesting of, well, you're learning for each state, action, next state, well, sorry, for each state, action pair, you have to learn a dice probability. And so each state, action pair partitions the input space, and the dice learning underneath of that handles the actual learning of the transition probabilities. And so it turns out you can quick learn an MVP, just from examples of transitions. So given that, what we're going to do is take that quick learner, stick it into a reinforcement learning algorithm, and it's going to be able to achieve the pack MVP test.
Can you boost the
I don't know. I haven't, yeah, that's an interesting question. So weak learners can be boosted in that model. No one's asked me that before. That's a good question. Think about it. I'm going to guess no, but the reason for it might be interesting. It might lead to something else. So put that up. All right. So so now imagine that we have some kind of class that we can quick learn. How do we slap a reinforcement learning algorithm on top of it? You can do this in a model-free fashion. This is an algorithm I invented for the purposes of this talk, but it actually has some reasonable properties. So here the idea is we want to learn an approximation of the Q function. One way to do that is to learn what's known as a finite horizon Q function for a long enough horizon. And the way that we're going to do that is we're in some state action pair. We take an action. We end up one step closer to the end horizon, but in some other state. If we know the value of that, if it's known because our quick learner says, I know the value, you can actually back it up and do almost like a Q-learning update to that value. If you don't know it, then you have to say, I don't know, and then this one doesn't actually get to learn anything. But what's good about this is eventually you're going to get down to the bottom, and everything at the bottom is doesn't depend on anything beneath it, and so it can slowly kind of, these blue regions are things that are known, they start to fill in from the bottom, and then the things above them depend on those, and the things above them depend on those, and by the time you get to the top, there might be very few things that are known, but the number of times it says, I don't know, ends up being proportional to how long it takes to learn. It's like a coin learning problem at each state action pair at each level. And so because of that, we end up with a polynomial bound on the number of times it needs to act in the world before it starts being able to make accurate predictions of the Q value. So it doesn't have to build the transition matrix, it doesn't have to build the reward matrix, it can actually use samples in the world as a proxy for the model. The world is its own best model, Rutgers. So this turns out to actually give a good quick bound. The reason that I was surprised that I came up with this for the talk, building on my students' results, I'm not saying I had this completely out of the blue epiphany, but this problem of can you make a model-free pack MVP algorithm was actually open for a bunch of years. We solved it with a really hairy algorithm that we call delayed Q learning, which is elegant and interesting, but it's really hairy. This one that I just described is much simpler and just builds on the insight that if you can quick learn it, you can use that as a module and build on top of it.
So it doesn't have any exponential dependence on gamma, presumably.
Depends on what you mean by that.
The horizon